From the campus of Stanford University.
People are worried about data. They're worried about their privacy and their security. They should be. We need secure systems.
This is the future of everything.
But we can't have a system that closes that data off. It is too rich of a source of inspiration, innovation, and discovery for new things in medicine.
With your host, Russ Altman.
Today on The Future of Everything, the future of using physics to understand biology and to build new devices. Now, when we think of physics, we often think of the study of fundamental forces in the world: gravity, the theory of relativity, electricity, the Big Bang, black holes, dark matter. We may think about the big experimental facilities around the world, big telescopes, particle beams and linear accelerators, the detection of cosmic events, black holes. We may not think, however, about biology. Biological systems, of course, must obey the rules of physics. But somehow those rules seem distant and not directly applicable in biological systems. We may not always think of a physicist studying fundamental forces relevant to biology, life on Earth, and creating devices for measuring these phenomenon. But of course, physicists do this. Indeed, life on Earth has had to evolve in response, I'm saying obvious things here, to the physical world to solve some remarkable problems. How do we encode the shapes of living organisms so that with just their DNA, with just their genome, they can reproducibly form their expected shape? How can living organisms work with water? Water is a fascinating substance. It has special properties in terms of its chemical makeup, its electrical activity, how it interacts with itself, and its ability to host other molecules that are dissolved within it. How can we build physical systems in living systems that perceive signals? How do we perceive visual signals, audio signals, touch, taste? These must all be sensed at a molecular physical level and then integrated into useful signals that the organism can then integrate to figure out the key things like where's the light, where's the food. That's pretty much everything. Where's the light? Where's the food? Where's the mate? So these are the basic functions of living systems. Now, a fascinating branch of biology is the study of how biological systems take advantage of physics to accomplish complex tasks that appear to be difficult or even impossible. So what am I talking about? Well, this includes the study of self-assembly, where individual units of a biological system can create a complex structure without any explicit instructions. Let me give an example. There are viruses, spherical viruses, that are particles made up of 180 identical subunits that form these beautiful, perfect spheres that contain the DNA that makes the virus infectious. Just based on how these individual proteins interact with one another, they can spontaneously form these shells. There's no need to build a scaffold. There's no need to say, okay, now you go there, you go there. They just kind of, because of their intrinsic physical features, they assemble with one another and they form these spheres. Similarly, the outer membrane of a cell, which is lipids that create a boundary between the inside and the outside of the cell, are made of lipid molecules that self-assemble to form these compartments that support the living machinery. Imagine having a bunch of fabric and saying, could you please make me a tent? And whoosh, the fabric spontaneously forms a tent. In the case of the virus, imagine just having Lego pieces lying around, which will spontaneously form a sphere without any effort. This is what happens in many times in biology. Or how DNA, of course, forms these beautiful double helices that look a lot like helical staircases. Imagine wanting a helical staircase in your mansion, not a problem that I have, where you just get all the materials and they self-assemble into a beautiful double helix without any instruction. We do not understand all the ways in which biological systems have harnessed physics to solve these problems, but we have examples where it has. This is worth understanding both because of natural curiosity of how biological systems work and because it may elucidate principles that allow us to take advantage of these same of these rules to build devices and new capabilities in our world that can advance our technology and our understanding. My guest today is Professor Manu Prakash from the Department of Bioengineering at Stanford University, and Manu is an expert physicist working on biological systems. He studies the physics of biological systems at the molecular, cellular, and tissue level, and he also takes the insights that he learns from this deep dive into the physics of biological systems to build cool devices. We'll get to the devices, but Manu, as someone who trained as a physicist, applied physics, what drew you to biological systems, and what do you tell your fellow physicists about what's exciting or challenging about biology?
It's once in a life you get this moment where you take a back seat and you think, what do you want your life to be? And that happens a couple of times in our lives, and that happened to me right after grad school. And anybody who's peered through a microscope would know that there is a piece of matter that we do not understand, that we cannot write down a bunch of equations to explain. And it's so us. Biology is so us. So, I was studying many different things in the past, but that emotional connection you have with, not only am I trying to understand this piece of matter, but my act of understanding it is that piece of matter.
Very meta.
Yeah,
Very
and
meta.
that's the philosophical times that you go in and then you ask, this is what I want to do for my life. And I think I find it's a little bit strange sometimes. You're right. I have to explain sometimes to my physics friends that, hey, this is the most exciting thing in the world. And sometimes I think that sense of wonder, if you just share that sense of wonder first.
Yes.
The aesthetic and beauty in biology is incredible. And if you're not working on a beautiful problem, then, find a new problem.
Now, I want to give you credit, though, because I know many physicists who they dip their toes into biology. They love mathematical equations that explain the world. If you've taken any physics, you know F equals ma. It's very famous. Force equals mass times acceleration. Based on that very simple equation, you can derive how we got men to the moon, how we build devices that work and that don't break. And sometimes my physics friend said, biology is too squishy. There's no right angles. There's no real underlying mathematical formalism. And I'm out. I'm sorry.
Yeah.
This did not happen to you.
Yeah.
Or did it?
Not yet. I think I'm naive, and I am perfectly happy being naive sometimes. And I actually tell most of my students, you have to be naive sometimes to have the guts that we will try to understand this piece of matter. And I think, to your point about the complexity, it is what makes biology so much more fun. That although there are these rules, there is every time an exception to that rule.
Yes.
And I find that fascinating.
So you have worked on this self-assembly issue. I talked about the viruses and some other things.
Yeah.
Tell us, what is the state of our understanding of self-assembling systems? And are we just at a baby point, or are we beginning to really understand what's going on when these systems do these amazing activities of creating complex objects from simple subunits?
Yeah, so I would argue we are really at the beginning. And the reason for that is most of our insights initially in that field have come from just watching biology. The fact that now we have the capability of really ripping apart a virus particle and really see the sets of components gives us the sense that we are starting to understand the list of components. But how they come together and build things that are not one, even 2 or 3 orders of magnitude larger than the component, like your example of truly bringing a grand staircase.
Yes.
From a point of view of a molecule, a cell is a gigantic staircase. We don't really understand where these length scales are set up. Where is that encoded shape and form at higher levels? Hierarchy has been really fantastic, so I think we don't exploit that too much and I think the other aspect of the field has really grown when we had tried to take small components and then ask ourselves, we are going to build something out of it. So, for example, the entire world of DNA algorithmic assembly, or even general ideas where you take and now make components that are literally dead, but still demonstrate the principles. That's where the most exciting bits that I see, because I start to see an inkling of things that we would never been able to manufacture before.
This is the future of everything. I'm Russ Altman. I'm speaking with Professor Manu Prakash about physics and its influences these days on biology. What is your favorite current system to look at to understand self-assembly? I'm trying to get this down to a real system that you find fascinating, that you think you might be able to understand.
Yeah, so this is kind of, it's slightly ironic, but sometimes what ends up happening is the biology inspires an insight, and then you can take that insight and even work on that system in an abiotic manner.
Non-biological.
Non-biological. And so there is a system in the lab that we've been trying to build now for several years to really demonstrate that we can do algorithmic self-assembly using droplets.
Droplets.
Yeah, there is 2 years ago we demonstrated a type of an active droplet system that demonstrates.
Are you talking about fluid droplets?
That's correct. Fluid droplets, but they can actually be phase droplets, they can be protein droplets, very fluid-like phases that demonstrate very phenomena that you would not be able to distinguish from chemotaxis, for example. They can sense each other, they can crawl, they can chase each other.
But they're not living. They're just
living.
Physical, literally small bits of fluid.
Of molecules of fluid, and they're communicating with each other.
Now that sounds like magic. You have to tell us. I have to stop you then. You have to give us a sense of how that could possibly happen.
Yeah, so you can do this in your kitchen. Go right now and find some food coloring in your kitchen and some water, and mix it up on a clean glass slide and put these two drops next to each other. In a few moments, you will notice that these two food coloring droplets will be talking to each other. What they do is they send out a water signal. There is a vapor cloud around it.
Vapor cloud, yes.
And that vapor cloud is interacting, and there is more vapor between the two than around the surroundings, and that leads to this incredible phenomena, which is not so far from retrograde flows in cells, where cells are these engines with all these motors moving around, but this purely arises in a physical system. And so the reason I brought that example is sometimes although biology is complex, the phenomena and the basic principles could actually be very, very simple in components.
Yes. So what I'm hearing from you, and this really does make sense, is that whereas we might say that because it's a living cell, it has a complex communication with its neighboring cell, you have shown that these two drops, which are obviously not living cells, still have communication challenges, and we may not need to invoke complex cellular communication to explain some of the phenomena that we see.
Yeah, and even to a point where not only do they sense, then based on that signal, you act on it, and you can move and you can sense quite literally the same phenomena that white blood cells are doing, trying to chase bacteria.
During an infection.
In infection, we replicate with 2 drops of water.
This is The Future of Everything. I'm Russ Altman. I'm speaking with Dr. Manu Prakash from bioengineering at Stanford. I know a little bit about your work, and I know that droplet work has also led to some intriguing demonstrations of doing computation with droplets. Can you give us a sense of what the heck? I mean, I think of computation as silicon, electrons, transistors, but you've written papers about how droplets can be used to to perform some of the functions that we traditionally associate with silicon and transistors. Tell us about that.
Yeah, so when we think of a computer, we're thinking of processing information, and that information revolution has led us here. But there is a bit that got missed out, which is that every bit in a computer is also physical. Every electron that's running around, you can make optical computers, photons running around. And I had this notion of thinking about, could we use computation to actually assemble matter? If that bit could be a grocery bag that I could put molecules in and other things in, run a computation, and voila, instead of getting a number out, I would get an object out. So that's been the mission for the last 12 years. I've been working on this. And at this point, we're at a stage where we have demonstrated universal synchronous computation using these droplets that interact with each other. They form all kinds of logic gates. They're completely modular, so the system is scalable. But the goal is not WordPress or word processing, but the goal is to actually build using this material. So imagine you write a little 2-line code that codes for the Sierpinski triangle.
Which I have no idea what that is.
So you can think of the Pascal triangle, for example, or you could think of a fractal.
Yes.
It's a fractal-like structure with a hierarchical structure. And if I was to place every element of that fractal one at a time serially, which is what 3D printing kind of tries to do, it would take forever.
But if you can teach it to do the computation.
It algorithmically builds, and local parts interact with each other to build a local structure that interacts with the rest of it.
So just to help us, I just want to go a little bit more for this computation with droplets. So is the right analogy that in the same way that we have wires with electrons moving on them, and we get the electrons to go to the left, to the right, and by bringing them together they can do adds or subtracts or other numerical, that you can get the droplets to flow through perhaps like a microfluidic channel, split, come together, and do very similar things as what electrons are doing in wire. Is that the general approach?
Yeah, that's a good basic way of describing this. And the droplets are interacting with each other just like electrons interact with electromagnetic fields and charges. They're interacting with hydrodynamic fields. And in the latest system we demonstrated there are no wires, that it's essentially a flat surface of water that they're moving around. And because they're interacting with each other, they provide the structure they need. And we inject energy in the system in a way to control it from outside.
Unbelievable. So we can look forward to these computational fluid systems that are helping us solve problems through an analogy with electronic computer systems.
Yeah, sort of my hope is that we're able to build some of these systems that can make materials that we've never been able to make. For example, heterogeneous material, like my hand, has thousands of different materials, multi-component. We're nowhere close to that in the context of our manufacturing capabilities.
So speaking of manufacturing capabilities, I want to move to the part that everybody loves when they talk to you, which is your focus on what we call frugal science and the creation of devices using the rules of physics, but with an extreme emphasis on affordability. And I think one of the first ones first of all, the computation with fluids could be that already. But let's move to something that got a lot of press, which was your creation of the fold scope. Can you tell us what the fold scope is and why it exists?
Yeah, so I think
we have one in front of us.
That's correct. We have something sitting here, and you should think of this as a pencil of microscopy. Many of us are carrying pencils and pens around, and it's important. It's a point of making about literacy that I can have my thoughts be heard and seen and share. It's a tool. And very much what ends up happening in science sometimes with, 2 billion kids on this planet and 1 billion of them technically living under poverty, it starts realizing this idea that access to science is not a common thing. We're just the lucky ones who sort of made it through. Somebody, helped us along and we're here. And billions of other kids can also be here, except at the same time, they haven't had the access.
And they don't have the tools.
There are a lot of knowledge, and actually the information revolution is really changing that. Wikipedia, Khan Academy, many of these miracles of knowledge. There's incredible knowledge. But science composed of knowledge and experience, and we're missing the experience. Without the experience, there is no aha moment. Without an aha moment, I wouldn't be sitting here. So what we decided to do almost 6 years ago now is to make a microscope that was going to cost $1 and can do resolutions that are subcellular. And there was this challenge of let's do something where cost and performance really try to push the limits.
Yes.
And this is where comes in new manufacturing tools. So FoldScope is an origami microscope.
So for those of you who can't see, we are looking at what looks like a bunch of cutout paper. It's colorful, and it has a bunch of cutouts.
And you should think of this as art and craft, essentially, that it should feel so natural to you. It's a piece of paper. You can drop it, bang on it. But then once it's folded together, There's a little place I insert a little slide of water that I just collected outside. I clip it on, and at this point,
He
I'm
is now
actually,
holding up to his eye this little piece of cardboard.
and I have transported into a new world. For a second, I forgot about you, Russ, because I was watching single cells of a moss, which is a plant-like structure, but except that little tiles of little pieces of bricks all assembled together.
So let me clarify. If I may hold that for a moment.
Yeah, I'm going to actually give this to you.
I've
So
lost him. He is in the microbiome.
hold here and here
Okay.
on the two sides and just bring it close to your eye, pointing to the light.
So let me just first describe that this is fundamentally made out of a kind of sub-cardboard grade paper, like what you might get a greeting card on. It's an elaborate folded piece with but in the middle there is something that's not paper, and I want you to because this is not
Yes.
magic.
Yes,
There's
it's
still,
not
I guess,
magic.
a lens. So
Yes.
could you tell us about the lens setup, what it's made out of, and is that an expensive component or is that not an expensive
No,
component?
so I think one of the questions we really asked ourselves is given constraints in physics, and this is why I call it frugal science, because there's a lot of rigor that went into manufacturing this lens.
I am seeing things in this lens.
And one of the threads that you start thinking about is given two optical surfaces, what is the theoretical resolution, best possible resolution you can achieve?
So you had to use pretty deep optical theory.
So we solved that analytical equation that took 33 pages to solve, but then once you have it, we have a design tool.
Gotcha.
That suddenly, and so rather than asking that I will keep piling up pieces of glass after glass, we asked a question, given minimal number of surfaces, what is the best thing you can do? And then we built robots. This would not be possible because at this point in the lab itself, we shipped around 80,000 of these instruments around the world.
How much do they cost?
So we, as a disclosure, we spun off last year as a startup company that I'm a co-founder of, and at this point, for $1.50, you can buy a Foldscope.
And is that an actual piece of glass?
That's
is
correct.
The
It's glass
lens?
lenses. It has magnetic couplers. It couples to your phone, so you can share the data with friends.
Now, for people who have used a microscope and they know that there's like 10x, 40x, 100x, what is this
So
x?
this would be equivalent to a 140x
Wow.
objective.
Okay.
And the thing that you start thinking about is the data that we collect I can watch individual bacteria. So if we had more time, I would have asked you to give me a little spit sample, and then we would have watched single bacteria swimming around. And
And the magnification is sufficient.
is sufficient
to see that.
enough to actually watch bacteria.
Was
And-
this motivated by a real health need, or is this mostly for the education of the youth?
No, I think it's both. And it was this realization that you cannot provide health services around the world if you don't provide health education. If you don't provide, I've been out in the field many times with a fancy hospital in the middle of nowhere, but the patients don't even believe in medicine. They have never experienced the germ theory, for that matter.
So seeing a germ might be a transformational
Yeah,
experience
and
for them.
So there is a social context to this, which is really we should open up science so people get a chance to really understand the beginnings, and at that same time, the same sets of tools that are Peruvian doctors who have used this for cervical cancer, we have demonstrated diagnostics applications for these, not just for humans, but for plants and animals. There is a sailor right now in the middle of the Pacific Ocean foldscoping on his 15-foot boat.
Unbelievable. Now, can you give me an example of what kind of diagnosis might a foldscope be capable of making?
Yeah, so any stool samples, for example, if you really start thinking about from the very beginning of where we started this, the question of helminth infections, eggs and stool.
You can
start
see
with
those.
urine. Absolutely. And I think one of the threads is we've demonstrated we can even image malaria parasites. We can image many bloodborne pathogens. One of the things that we have just...
And I want to stress, when he says image, when you say image, you're talking about with this $1.50
Absolutely.
cardboard plus a piece of glass and a piece of metal.
Yeah, and one of the things that's valuable about diagnostics when we started doing this is we realized diagnostics is about searching for a needle in a haystack. And sometimes if the needle is right in front of your lens, you get to see it, but sometimes it's not. So we invented a way around that to find the needle.
This is The Future of Everything. I'm Russ Altman, and I'm speaking with Manu Prakash about how physics can turn into extreme frugal instrumentation. So you were just about to talk about a new device. I believe it's called the paperfuge. What's the paperfuge all about?
Yeah. So it sort of stems from this idea that if you're searching for a needle in a haystack, if you could just pick out the needle, then you won't be searching anymore. And that process in the scientific context is called centrifugation.
So that's usually, I think of a big machine that spins very fast and it separates. The thicker things go to the bottom, the thinner things stay at the top, and we are able to separate.
Yes. And so by density, and it turns out parasites have different density than our native cells. So if there is one blood cell that has a malaria parasite, the density has changed now, and we'll be able to pull that out.
By separating?
By separating it. But now the question is, if I'm in the middle of nowhere, under a tree, with no electricity, no power, no nothing.
Then that big centrifuge that I described is not an option.
That's correct. It's not an option.
I'm looking at Manu, and he's holding an odd-looking thing, which I'm sure he's about to talk about when I shut up, but it looks like two cylindrical cardboard pieces with string and then something in the middle. What are we looking at, Manu?
You are looking at one of the oldest toy in the history of mankind. This is a 5,000-year-old toy, which in many cultures is called button on a string.
Button on a string.
And we made this realization that if we study all possible toys that spin, could we mathematically write down equations to beat the world record for fastest spinning object with human power?
Human engineered. Oh, and human powered.
Human powered. So we have this object that I'm now spinning.
It is spinning very fast. He's doing kind of a back and forth motion with the string, and the central disc is spinning, I have no idea, I'm sure Manu will tell us, very fast.
Yeah, so this specific one right now itself was spinning around 20,000 RPM, 20,000 rotations per minute.
Whoa.
And then there are many versions of this we make, and our fastest spinning one is actually 125,000 RPM.
Now, does that actually set the record you were seeking?
That is correct. That sets the world record at this point for the fastest spinning object. And I think the reason I'm stressing this is I really do want people to break that record.
Right. It's a challenge.
It is a challenge. And, of course, it took us, again, going back to the rigor, 20 bits of equations to really describe the parameters. Because although people had played with this toy, nobody had asked this question, how this toy actually works. And so, the joy, going back to the beauty in science, is the joy for us was really figuring that out. And, of course, there is a phenomenal outcome of that. But I would have been happy just figuring out the toy as well.
So we set the record for rotations, but I guess it begs the question, are we able to use this device to do the kinds of separations you described to actually make some kind of useful diagnoses, find that heavy malarial cell, if you will?
Yeah, so I think they're in here, if some of you can see, there's a little glass slide, a glass capillary that I had put. And if we had more time and I had my lancet, I would have done a little finger prick, take the capillary, fill the blood. Within 90 seconds
of going back and forth, with that little whirring sound,
we have separated all of blood plasma from the blood cells itself. And pure plasma is extremely useful and important for RDT tests, all these rapid diagnostics tests, because all the enzymes...
You have to get rid of the red blood cells, and you want kind of the clear fluid that's left.
You get this fantastic sensitivity and specificity using that. And then, of course, if we just spin for a little bit longer, for around between 7 to 10 minutes, you actually separate out every single malaria parasite. Malaria is a tough one because it's a really tiny parasite, but that in itself, this thing is spinning around 30,000 G forces.
30,000 Gs.
G, that's correct. So you are experiencing, if you were that little cell, you're experiencing a very high force.
Well, this is just fantastic because we've gone from a very, for the lack of a better phrase, highfalutin conception of what physics can bring to biology to a series of inventions that are bringing science and the ability to make experiential observations really globally to everyone in the world who has any interest in doing that. Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.